Welcome back to Season 3 of the ZK Whiteboard sessions. Today we'll be talking about trusted execution environments. I am Guillermo Angeris, I guess Chief Scientist of Bain Capital Crypto, and we have Andrew Miller. What is it? Adjunct Associate Professor.
That's right.
Back in the day at UIUC. Now, I guess, what do you do? It's like a grab bag combination, of stuff.
That's very focused. I'm a junior product manager at Teleport.
Oh, good. Okay. Oh, junior product manager.
Incubator.
Okay.
Well, yeah.
Good. That's. I think it's it fits the position coming from professor down to the junior product manager. I think you learn new things along the way or something.
Yeah, exactly.
Like that. Oh, good. Okay. So, anyways, today we'll be talking about TEEs, which I'm very curious about. I don't know if you have a rough outline of what we're going to be talking about today, or if we just want to get started. Totally up to you on this one.
I bet we can make one real quick.
Okay.
I do have a rough plan in mind, but I expect you to help on, massaging this outline as well. I know that at least I want to start with a little bit of like a high-level trust model and like the basic model of like what is a T, where it comes from, that sort of thing. I know that I want to get into like some application examples. I think that one of the highlights of this, but I think that's going to come like maybe 3. Is going to be the coprocessor model and an auction. I think this is
okay, cool.
Can go through. I bet this is going to be kind of the natural second module break, because I like this because we can go into, I think, like in detail how you construct like a good application that makes use of everything that T's have for pretty clear application motivation. Yep. I think I'll go through an auction as a motivating example, how to do a secure auction in the TE coprocessor model.
Okay.
And I want to leave some time to go over, what do I want to say here, pitfalls in security mindset kind of things, especially the ones that are, we'll get into kind of the trust model details. A lot of this, the main kind of principle of T's that makes it, controversial in Web3 is that it's not just that there's stuff for you to do, this is stuff that's made by, hardware developers. Yes. It's not like ZK where we can go learn the math and go, fix all of it ourselves. We're kind of beholden to, hardware manufacturers for part of it. So a lot of this is just understanding what goes into the trust model, under what circumstances do we believe in it or are okay with it, that sort of thing. Sure. But I do want to talk about like software security pitfalls, because those are the, my best outcome out of teaching like this is get a bunch of people building applications, building software components on top of this. And then there's a lot of, you need to be mindful of a handful of security details. And actually, just as the placeholder for this, really the 2 main topics are side channels.
Sure. Yeah, definitely.
And replay or rollback attacks, kind of like statefulness issues. Mm-hmm. And maybe this will end up being the last thing is, upgrade processes. There's actually a bunch of things to say here. It's actually a lot like smart contracts, like it's the it's not the T that brings this, but you have to think about immutability, or like the flip side of immutability of upgradability, and then that's like a tricky thing to get right. So this will have a bunch of like, detailed stuff to talk through.
Yeah, well, so the side channels and replay attacks do feel, somewhat akin to parts of many cryptographic things already.
Yeah, so. Absolutely. It's not, fundamentally different, but you have to consider them kind of, with extra importance. Or really, I think it's like you get to the point of this being the bottleneck there because you get to take so many, speed up improvements and kind of developer simplification relative to other crypto stuff. So you get to the upgrades being, the real remaining sticky thing when working with T's a lot.
Very interesting. Okay.
And the second bit will be going in through some details of like SGX and TDX attestation specifically. I will draw on the board like the visual aid of like what you get in the attestation certificate, and then that also serves as kind of a checklist of all of the things that are worth talking about, because those are all the things that you have to, inspect as a client, or that form part of your audit surface if you're an auditor looking for these. So my guess is that we're going to break this into sections maybe along there.
Perfect. That sounds great.
Maybe it'll even be like that. Yeah.
Sure. All right. So let's start with, I guess, the high-level trust model. Yeah. So. I guess we're not going to be talking too much about hardware today. We're going to be talking more about like idealized models, but there is some stuff that, like you mentioned, there's a difference between SGX and what was the other one I believe you mentioned?
TDX.
TDX.
And there are a bunch of others as well.
Sure.
like Intel, part of why this is this works, or what we're talking about is it's something it's not even a new kind of hardware. It's basically like a feature that's already present in most of the processors that you have. That kind of takes a while to kind of acclimate to. So like if you buy both Intel and AMD server processors, not like all of them, but maybe like half of them or something have support for trusted execution environments. It's not even special hardware, but it's like an unusual execution mode, or like a less known, execution mode. So it's just an execution mode present in your server class processors.
Very interesting. I always assumed that like TEs were, like a little black box sitting somewhere in some core of a processor or something separately. And then, I know that that's kind of the mental model that we should have, but in reality, the implementation seems to be pretty different. So, okay, so anyway, so we're going to start with defining the high-level trust model and what the hell these things mean.
Yeah.
And how does it work? Okay.
So the basic kind of four parties that are relevant here are the manufacturers. So that's like the your Intel, your AMD processor companies that build processors with TEE support in them, right? And then the execution environment refers to this like secure operating mode. Really, there's two main features that I think define TEE. So the first one is isolation. The basic gist of what this does is that when you run, familiar with like kernel mode and like user mode, this is something that's supported by processors. It's not just the operating system defining it. The processor is aware of like different processes having different access to different parts of memory, that sort of thing.
Like the different rings, for example.
The different rings, exactly.
Right. So, sure.
Where like the lowest ring, actually I think hypervisors are sometimes regarded as like ring -1 because like super user was already ring 0. And so, have like a, even above that is kind of like ring -1. You can kind of think of T as like another ring, but it doesn't quite fit into the hierarchy, right? Because those rings are always like everything at a ring below
it's containing
and control everything over there, right? So like a user process can't defend itself against the root kernel reading its memory, and the hypervisor can read, the things of VMs. So it's not right to say that TEs are like a ring -2, like below hypervisor. It's actually a little bit different. If anything, it's actually like a kind of, side quality that makes even your user processes defended against the hypervisor or the kernel being able to inspect them. So it's almost like protection in the other direction.
Yeah, so it's like instead of a total order, we have like -2, -1, 0, 1, 2. We have a partial order, I guess, somewhere where the like... or the TEE lies.
Yeah, so that's the gist of it. So when you run a program or a VM in TEE mode, it's isolated from the hypervisor, kernel, other processes. It's completely isolated. Nothing else can inspect its memory. So that's what secures it against other tenants, other user processes, and even people with admin access, root access on the machine itself.
I see.
The other most important feature that TEs then provide is remote attestation. We'll like unpack this in a little bit and go into more detail on what exactly that includes. But basically this gives you a signed certificate generated by your program running in TEE mode. And in this signed certificate, it's got like a chain of signatures that goes all the way up to the manufacturer's public key.
Okay.
And in the body of the certificate, it includes like the program that's running, like the hash of the code that's running, data that it outputs, like application-defined data that it outputs, and some other details like the configuration of the processor that's running. So the point of this is that, I guess I put this right in the middle of this, and that wasn't really what that's meant to be. That's kind of okay. I did mention that the manufacturer has a public key.
Yes.
It's going to be important to come through. We'll get into this trust model kind of difference a little bit, but this was going to be the hosting provider or cloud. Unpacking and understanding the trust model and its nuance kind of is going to involve like the interplay and reputation and other kind of soft stuff, but between this like separation of roles there. And the key thing is like who is going to be checking the remote attestation? Well, end users who are going to be deciding to share sensitive data with an application on the basis of knowing this is going to be an open source program. I know that it treats my data, safely. It doesn't just output it. I'm going to look at this remote attestation to get confidence that the thing I'm sending my data to is running a program, is running the program that I think it is.
Got it.
If you rent a cloud and like run a service on the cloud, and your users, connect to this service, they have no idea what code you're running. And even you say, oh, well, I'm running this open source code. Here's our GitHub code. And users connect to this service. there's no way to know that there's a connection between the service there. And it's even kind of tricky because like the account owner, like the one who owns the cloud account, like they have a business contract with the cloud, right? So they have some standing, like they're not going to be, screwed over by the cloud. But the random website visitors that go hit, the EC2 IP address, they don't have a business relationship with the, EC2. So it's like, whose side are they on anyway? I mean, so normally the cloud isn't like inserting itself in the middle between the, app developer and users.
Sure.
But in a way, that's exactly what we want, right? So it's like this whole viewpoint to me is kind of like with Web3 mentality and values and expectations and trust model, with like disintermediation and like low barrier to entry for developers being kind of the key point. And largely, it's about basically inserting this manufacturer and hosting provider system together in between app developers and the users or relying parties. So basically, the users get to like they get to, what do I want to draw here? Well, clearly, like the users directly connect to the system running in here, and they do this based on interpreting either by themselves or auditors that they trust the code that describes the application. But they don't just have to take the developer's word for it. They basically get this chain of certificates from the hosting provider and the manufacturer that say, this is the program that was running when you interacted with the server at this time. So that's why you send your encrypted bid into an auction. It's going to be treated according to auction rules and not picked apart and peeked at.
Got it. Yeah. So like even higher level, the like very simple mental model I have for this stuff is still, funnily enough, this black box thing. So like, I am whatever AWS 0.2.
Yep.
Right. I have a rack. Right. And then someone's like, cool. Developer wants to run, or some company wants to run some code on this particular rack. Like in this rack, there's like this magical black box that says, if you run code inside of me, I can make certain guarantees so long as you trust the manufacturer. And those guarantees could be anything from, you can make certain guarantees to people who are not, me, right? So like, for example, you come and connect to my like cool, rack. You connect to this particular black box, right? And in there, if the developer is running code in this black box, the little black box says, I can guarantee you, Andrew, that like, I am indeed running the code that the developer says I should be running. And, depending on whether you want it, right? Like I, Guillermo Angeris, like who runs this cool, rack in my server, cannot read the thing you're sending to this black box, for example. Again, there's some trust assumptions here between if you trust the manufacturer of the black box and things like that, but like fundamentally, that's, I believe, so that incorporates isolation in the sense that even though I physically have the box, right, I cannot, essentially I can't like mess with the program that the developer has put in this black box. And the remote attestation point is, you, Andrew, can check that like the code is indeed running in this black box, and if you trust the manufacturer and all this stuff. So that's like my very dumb mental model of it. That seems to be roughly correct with here.
That's exactly right. Yeah.
Okay.
I mean, so the developers like own the account at the hosting provider, right? But themselves aren't installing the box. The hosting provider that installs and manages the rack run the processor that they've got and aren't involved in the public key consortium of that. I mean, the limits of the trust model, maybe just to go straight to this. So this manufacturer, like certificate kind of system, certificate chain of signatures involved in remote attestation. It starts with a public key for, a long-term public key associated with Intel, if it's like the Intel chip.
I see.
Clearly, like Intel could use the private key to that to sign, fake remote attestation. So the first level of trust model is you have to trust them not to do that. Although if you also, as a relying party, are checking the system that comes with like a signature from Azure, as well as the underlying remote attestation signatures from Intel, then it's like both of them would have to be, making use of that to basically dupe you into using a fake enclave system.
Wait, sorry, repeat the last sentence. So if I have Azure and I have Intel, what is the, like, what do I have to not trust for this to be the case?
You'd have to trust both of them colluding, essentially.
Yes. Yeah. Okay. Sure. Yeah. Right. Which it hopefully is unlikely. We don't know, but like that seems fine. Okay. Cool. And then there's some way. So long as like I know that the Intel has not formally colluded with AWS to sign bad boxes, like we should be good. Which I think is a pretty reasonable assumption, maybe.
Yeah,
but
roughly that's it. Yeah.
Okay.
Yeah, this isn't a bad section to go into, more of the like philosophy about that, just because the other security and trust model stuff I, end up wanting to spend the most time on is kind of into the weeds on like what the application developers have to bring and, worry about themselves. So, I mean, it's okay to kind of go and, unpack some of those. I guess another thing worth mentioning is the idea of threat model and physical attacks. And maybe this will also come up a little bit later because I'll draw, what do I want to draw here? Actually, this is probably going to be an okay time to draw this bit. There's two kind of main paradigms for this. There's process-based TEEs and VM-based TEEs, or confidential VMs.
Ooh, okay. I have no idea what the difference is there. Okay.
SGX is kind of the main example of process-based. I actually think that ARM Trust Zone is not exactly a full system where it comes with the whole like signature, like OEMs have to be involved in like using the ARM Trust Zone things. It's a little bit more of a kind of a different thing. Whereas like with Intel and AMD, it's like that manufacturer kind of sets up this whole system.
Sure.
So like SGX was this process-based one. Same with Trust Zone. I guess Keystone is like a Berkeley, open source research project kind of thing. It's not like you can buy it. It's not like a finished production thing, but this is also process-based. The newer trend is confidential VMs. So if you see AMD SEV, that kind of works like that. And then Intel TDX. This is the one that I have the most experience with and use the most now, is of this kind. And so these are very similar. I guess this is now like another way of illustrating this kind of like ring idea. So what you have is this TE execution mode. All right, and then you also have the untrusted, environment outside of it, and so this interface between the trusted component and the untrusted everything else is like the most important, thing to start thinking about the trust model and limitations and what, pitfalls to worry about in architecting something based on this.
Okay.
So in the process-based like SGX, the kernel is untrusted.
Sure.
And an individual process runs in enclave TEE mode. And one of the consequences of this is that, the TE can process stuff. It runs a process. It can run code instructions. It can access memory. I mean, even then, actually, like, main memory is somehow, what do I want to kind of draw about this? The main memory is encrypted in a TE situation. So, like, in a sense, the boundary of the TE is the processor chip.
Yep.
The memory outside is going to be encrypted. And basically every time memory is, a cache miss occurs and memory is loaded from main memory into the processor cache, is when it gets decrypted, getting decrypted by a key that only the TE process, can have. So the kernel itself, even though the kernel should be, ring 0 very powerful, is not able to go like decrypt the memory. And even the kernel cannot like open up debug mode and like look at the TE process while it's running and copy the decryption keys out of it.
Got it.
The processor's support for this like prevents even the kernel at ring 0 from interfering with a TEE process.
So one way I don't know if this is right? Like the processentially version of the TEE is we have one ring lower than I don't know if this is right. But one ring lower than the kernel, and that is enforcing that the kernel cannot, for example, access specific parts, or is that not right?
I mean, it's not right only because otherwise there's this like, otherwise it's like, user, kernel, hypervisor. The relationship here is everything below can read and modify everything at the row after.
Yes.
All right, and so with this kind of notion, you almost need like a, 1 star or something.
Sure.
Because this TEE process can't read the hypervisor, so it's not like a TEE process is below and gets to like control, meddle with everything else there. Still kind of, in a way, it's like lower than user space mode. It like doesn't get special privileges to go access the kernel. But also it's in this kind of side area where even the hypervisor, even the kernel can't go dump its
so the
contents.
hypervisor also cannot. So this is like...
It's kind of, to the side.
Yeah, I guess I'm even dumber question is I'm trying to understand, in other words, what type of like object this thing is relative to like the processor itself. Right?
It's a process. I mean, how would you, the same way, like, I mean, if I say what's calc.exe, like a user process, what's the relationship between a user process, the kernel, and x86 code on a processor?
Sure. Right. But the process has to be kind of like, there has to be like some sort of flag or something, which essentially enables this.
Absolutely. Yeah.
But like what part of the processor essentially enables that flag? Or not enables the flag. What part of the processor, if that flag is enabled, prevents the kernel, for example, from accessing those properties? Like
memory manager, essentially.
So so there is a memory manager. It's like some very low level code that's running on the processor, essentially enforcing the separation. So like the dumb way I think about it, if I may, is like I think of it as like, this is the dumb partial order model, I think, of the DAG, and then I think of it as this, right? Or I don't know if it's running the hypervisor. Maybe it's -2. So maybe it's this, right?
Yeah, but again, I mean, if these arrows would indicate that the kernel, a user process cannot hide from the kernel.
That's right.
The kernel can absolutely like overwrite pages of code in the user process.
Correct.
Fully under its control. Same thing with hypervisor. It can interfere with those.
Yeah, but like
and so this error is not true. Like even even
the microcode.
Well, yes, I see what you're saying. That's kind of interesting. This is a very like graph theoretic sorry. This way of resolving this kind of thing. Yeah, there is no code that runs at this -2 level. But if you imagined a sort of like virtual -2 level there that is inert and doesn't do anything, that's fair. Yeah,
okay, so
at least this is fair.
So there is no code, but there is like a piece of hardware, for example, that enforces the separation between these kind of standard rings.
Yeah, exactly. But it's just I think of it not even as special hardware, but it's just because even in the pre-TEE world, you still have processor support for isolation that keeps user processes from interfering with each other.
Right.
That is still managed by the memory manager. And now the memory manager is upgraded to be aware of this extra set of flags that processes this isolation.
Okay. Got it.
Uh-huh.
Okay. So
that's really the way to think of it.
That's cool. Okay. I think I get it now. Okay.
Yeah.
Cool.
That was fun. Okay, and so I mean, this is in this like process world.
Sure.
Now in the VM world, it's the really similar thing. Only here you have a VM. So processors also have virtualization support. So the reason why like VMs work so efficiently is because like Intel processors are like aware of VMs. Mm-hmm. It's not just like software virtualization. The kernel does like the processor supports it. So it has a node, which is why the like -1 and like hypervisor is sensible there.
Sure.
So here you have a confidential VM, or they say a CVM for that, and it is just like a virtual machine. So it's like a virtual 0 on the hypervisor, but it can be in TEE mode, and then that prevents even the hypervisor from being able to look at it, debug it, tamper with it once it's launched and running.
Got it.
And what you still then have is that the hypervisor on the outside is still untrusted. So we still say untrusted hypervisor.
Okay. I see. So yeah, in this model, essentially, we're like, instead of enhancing the memory access / like paging and all that like fancy stuff that like happens in the processor, and enhancing that with like the ability to rate a 0-1 flag, we're going to actually use the virtual machine machinery inside of the processor, and then have it kind of enable this sealed off, isolated environment from the surrounding context.
Mm-hmm.
I see.
Yeah, that's exactly right.
Okay. I think I understand the high level difference, but
so what do you think about the interface between these and the untrusted kernel and hypervisor? So like you can pick either side, but
oh man,
I guess I have a couple examples in mind that I think you might come up with. But like what could go wrong, right? So the problem is untrusted, right? So our threat model is a malicious hypervisor. Mm-hmm. So we think that whoever is the hosting provider or a sysadmin in the hosting provider is manipulating whatever they can at the hypervisor level in this VM approach or in the kernel, whichever one you want to pick to try to make up some answers here. They're malicious, so this untrusted code is trying to run in tamper mode to the best of it can.
Okay.
In order to try to either learn something that it shouldn't, that was meant to be kept private from this, or to tamper with the execution, make it do something, integrity failure that it wasn't supposed to be able to do. Mm-hmm. We already covered that the memory is encrypted. Mm-hmm. And maybe implied in this is also authenticated encrypted.
Sure, fine.
So you can't just like write and tamper with the memory and have it like, so if it tries to read something and it's wrong, it would say it was invalid.
You can't just like randomly flip bits in memory or something and be like, yeah, sure, we're totally cool, fine. I mean, one thing that jumps out at me is, like, even though the memory is encrypted, you probably know what parts of the memory you're able to access or not. I don't know if that also, I assume this also happens in the VM case, right? So you have this property of like, when things have been stored in memory and when they haven't, when,
Yeah.
although you might not be able to read it, you can always say like, okay, here, I'm going to try to access this part
Yep.
of memory. And then it just like, the system gives you an error, says, sorry, you can't do that. But now you know there's something there.
Yep. So
Right.
the kernel's responsible for paging, right?
Right.
So there's virtual memory. So the actual amount of memory you
that's
have
right,
is
right.
much smaller than the total kind of expressible virtual memory space.
Yes, absolutely.
If the kernel has
That's right. I forgot the
pinned all of the
kernel.
memory, like it has
Yeah.
physical memory backing all of the virtual memory that a processor expects, then even when there's a cache miss and it needs to go read from memory, kernel isn't involved. But when memory's unmapped, then the kernel gets a page fault. And what this looks like in SGX is control transfers from the TEE mode isolated process to the kernel, and it says this is the page of memory that was being requested that caused this page fault. So
I
yeah,
see.
that's the first and kind of, to be honest, kind of skips us all the way to here and gets
Sure.
the main point of it, which is, everything that goes through this untrusted interface is going to be leaking some amount of control. The memory is going to be encrypted, but it is going to be revealing if the kernel, aggressively unpages. One way to do this, actually, there's a name for this and a pretty good research paper on it called controlled channel attacks. And
Sure.
the control
Okay. Yeah,
in the
that's a cute
control channel, the control refers to unpaging all the memory.
Yes.
So the kernel can just say, screw you, I'm unpaging all of your memory.
That's right.
Now the next, and it's even worse than you might expect because it's not just the data memory, it's like the code, because the program code,
program itself
whatever.
is supposed to be running until you could get branches, for example.
So I learned
right, that you hit.
I learned roughly where, to some granularity, where in I unpage all the memory,
Yep.
the next instruction count hops to some page of code. That's
Yep.
the page, it tells me roughly where the code pointer is.
Right.
So I can read,
Yeah, you can probably get some sort of branches, especially if the branches are large. You could know where you end up in certain parts of memory if you like break and jump to some point, if you like terminate some loop and then
Yep.
have some other condition. So certainly, yeah, you leak quite a bit of information because the kernel, unpages everything and then of course has control.
There's another
to
really cool
which
paper
which
that's
it works.
just,
Okay.
won't go into detail, but it's directly responsible for, responsive to this called A-exit notify, which basically for asynchronous exit, which is like what happens when you get a page fault out of the enclave and then control returns. Ordinarily, or the way that it used to be, or optionally is, but unless you use this new thing added for security, when control goes back to the process because the page fault was handled and some memory is now paged in, the process just resumes right where it was as though nothing happened. Like some time's passed, the buffers are empty because whatever I cleared cache on the way out, but I just keep running as though nothing had happened. And AE-exit notify lets the enclave be notified that this happened, so
okay.
it can like keep a counter and being asked, the 10th page fault and I haven't made any progress on my multiply, so like
Yeah,
being attacked,
something's
turn
weird.
off.
I
Yeah.
see. Very cute. Okay. Okay. Very interesting.
This happens with memory. That's kind of the important thing. If it happens for memory, obviously that happens with disk as well. Like the
Sure.
disk is external and you can't get to the disk except by kind of
kernel.
permission through the kernel. All of this is true in the hypervisor as well. It's a little bit different.
I was
You
about to
still
ask. I
have
mean, I
the-
feel like VMs still have this particular problem.
there's still a VM notion of a page fault.
Sure.
It's not as common. Like the kernel is like super like swappy and involved. So like there's a lot of like transfer back and forth between
Yes.
the kernel. Like on an interrupt timer, the kernel will be interrupting processors, letting them go a lot. At the VM level, it's way more set and forget it. You tend to just give like a big range of of allocated.
You just like slab allocate a bunch of memory. Right. Okay. Yeah. And then ideally the VM hardware is handling, how to actually do the rest.
Yeah,
Or
exactly.
Specifically
And
the
now-
kernel inside of the VM too, but
Exactly. Yeah. And so now
I see.
yeah, exactly. That's basically it.
Got it. So yeah, so this prevents here if you want to switch also.
Okay. Yeah,
Give you
maybe for a
bit
little
more
bit.
space too. Okay. So yeah, in the VM model now, of course, you still end up with disk access, right? That still has to go through the kernel unless you partition
The kernel, although now the kernel is part of this. The kernel is
Right.
inside the TEE.
Right. When you have a VM, do you also allocate disk specifically to the VM? No, you don't, right?
I mean, what you will do is attach like, virtual device kind of, pass through.
Sure.
So the VM has a way to kind of request it, but it's still like at the discretion of the hypervisor. I think the hypervisor has to get like woken up each time that it is accessed. Certainly, like it's able to, the hypervisor can present like a virtualized disk
Yeah,
to
like
it. There's no way to know it. Now, what you will do is use full disk encryption.
Right.
So the key to decrypt the disk is going to be managed only within the confidential VM.
Sure.
So still kind of same thing as the memory, like page by page, I can't, tamper with anything. And I can't see the contents of it.
Right.
But I can definitely set it up where I learn which page of disk, which block of disk is being accessed.
Right. Although I'm sure you could, if you have a small enough set of things in there, you just memory map the whole thing, and so everything is kind of in your allocated slab at CVM or something.
Yeah, that's right.
The
the hypervisor still has the ability to, lock pages and kind of set up the same thing. So like I guess what I would say is that with the kernel, the average kernel, like the standard Linux kernel, is like way more actively involved in paging things, whereas the standard hypervisors are way more like set and forget it. But a malicious hypervisor can still like pause pages and set them up where it has to bounce back to the hypervisor in order to access. So that that kind of channel is still there.
I see. But it's just one layer lower, which is more annoying to access, for example, and you probably need to like do some stuff where you root the processor, and then when you update the BIOS, you have all sorts of nonsense. I see. Okay. And then essentially your point here is like everything is moved mostly from here, although there is some stuff here, to confidential VMs for a lot of these reasons.
Yeah, absolutely. Well, so the programming model for SGX used to be really difficult. First of all, there's a complicated interface because what do you want to say here? Just this interface between processes and the OS is kind of a lot more involved. And you have to define these like entry and exit points for the enclave. I guess even actually I spent a bunch of time doing SGX programming with Grameen. Grameen is this really cool framework that basically takes arbitrary compiled binary code and we can do it two ways, either at the interposing at the the libc level, or it can just be at the system call level, and it basically turns system calls in the process into O calls, meaning calls out to the untrusted operating system.
I see.
So this is kind of like a portability layer that makes it easy to port code to that, and so it was getting relatively easy. You could get 90% of the way towards stuff just kind of porting over without thinking about it too hard. Some things would still be kind of difficult, like shared memory between processes wouldn't be supported with this. So some things would be kind of difficult.
Sure.
For kind of like a silly reason, Go not using libc made it where you would have to trap the system call every time that a swap is there.
That's
so
right.
Go code would tend not to be very efficient with this, whereas other ones would be.
I see.
Still kind of caveats. And then on the other hand, when you bring an entire VM, everything goes much more easy.
Right. Everything is purely containerized in this thing, and you can change whatever you want, right, about it or whatever. Which is quite easy.
Exactly. When you have to bring a whole kernel, it also means that now the software developer has a much more, kind of code challenge that they have to bring. If you bring a whole kernel, that's kind of a lot of attack surface. There's bugs in kernels a whole bunch, and now this turns into stuff that could be exploited. So if you call the TCB the trusted compute base, is everything that the developer downstream of the TEE system brings in, then they kind of have more responsibility here with the VM.
Right. Yeah. So now there's a question about tooling and all this stuff. Okay, now you have to have a trusted kernel, something that's reproducible, and all this stuff. Okay, I think the model's pretty clear. I'm curious about, maybe we can, finish here first for a sec, and then we can talk about the attestation part, which I think, I don't know, unless you want to say anything else about the high-level trust model.
What's else good to say here about the high-level trust model? We can maybe talk about physical attacks just kind of briefly. So back to kind of the philosophy and part of this. So the threat model that all of these are designed for is basically the software model. So it's very much like thinking in terms of these software control layers. I think the gist of this memory encryption is kind of important. There's a paper that I like a lot called Membuster, which basically describes how to use a memory interposer, which is you have your RAM chip, right? I don't know if this drawing is going to end up making any sense at all. Does that look like a stick of RAM?
It looks like a roughly RAM chip. I mean, I'm assuming that this is, Trent's, this is we've cut out apart, but.
Yeah. And then this is a memory interposer.
Right.
All right, and this is hooked up to like an oscilloscope or something, kind of a display. I call this like a game genie for your, your RAM. Like you get this as like some test equipment or something, and basically now even if you do this like AE exit notify kind of thing, if you are like reading with this little like inserter, like a copy of every, the data is still encrypted, but the locations being fetched are visible. And I believe that here now it's actually also not just the page level, but also the, I don't know, the cache line specifically. So maybe even like more fine grained. Right?
Yeah,
there's nothing in the system that prevents this from being, visible. Right. So essentially you have to be trusting the hosting provider not to be doing that.
Sure.
And I guess Intel can't tell whether they're doing that. So that's just having to trust the hosting provider.
Yes. Essentially, any like passive observational attack, you're going to need to be trusting the hosting providers, as far as I understand, right? Because obviously, like they could put, between every wire and the PCB or something, certainly they could put, a digital oscilloscope or something.
Yeah, exactly.
So RAM is a natural place, but you could imagine all sorts of stuff happens if you. I don't know, in these like fancier systems, you can imagine having, systems where it's not just like a processor with RAM, but you actually have more complicated things like handshakes between different pieces of hardware might like also be legible for some reason or another.
Yeah, absolutely.
So, okay.
Yeah, close enough. This was going to be kind of like high level and hopefully, barely fits into there, but it's kind of a short little exercise. I have some in mind. Maybe you can fill in others. So one of the appeals of especially the confidential virtual machine is just how really readily available you can get any code that already exists, like legacy code, not written with TEEs in mind, can at least be made to run in a confidential VM, and therefore you automatically pick up some privacy benefits and integrity benefits, and if you use them together, you can also do like distribution and failover, like build a decentralized network basically out of any existing legacy code. Right. Modular that you still have to like consider, these things like side channel and replay attacks, which we'll get to later in terms of the disk and network and what kinds of things are leaked to the untrusted environment about these. You can basically play this game of like, if you put in some legacy code that does some kind of thing, what decentralized application do you get out of it, and how well does that go?
Even depending on how you like hash or something, you could do like weird private like Bitcoin stuff or something, right? That's kind of
absolutely.
I mean, like within the TE trust model type of thing, but.
So one thing that you can do is have, say you put in say you have a roll up, so you have some sort of like, fraud-proof based roll up.
Sure.
Right. When you put it through the TE process and what you get out of it, you basically get this remote attestation evidence that a block that's produced by, sequencer in this roll up is valid. So it's almost like you get a proactive proof. What would be the right name to call this? Would this be like a T validium if it's something like that?
Probably. I actually don't.
I'll guess that it's like.
I don't have the cool names.
That's not the cover here.
It's very possible.
Very well, maybe. Okay, we'll discover in later episodes exactly how best to classify with this. But basically, you can go from a retroactive proofs only to now, a proactive, proof of it. So, justified for having the, finality in some way. I don't know if you saw this Ethereum Magicians post kind of recently, but Vitalik has a post really recently on how TEEs can be part of a stage, 2 or stage 1 roll-up.
Okay.
It's in a very nuanced way, and maybe I won't get into that. It's not that you just rely on TEE for finality directly, but more like you could rely on a TEE for if you have a security council-based, interrupt mechanism to like halt or apply a security upgrade to a roll-up, to count as stage 1 in the Ethereum framework for these, the security council has to wait 30 days for their action to take effect.
Oh, interesting. Okay.
But if you instead use a TEE proof of bug, I'll just call this proof of bug. Sounds kind of silly. That's not the phrase used, so we make that up here.
Okay.
But TEE proof of bug. You can use the TEE proof of bug to justify the Security Council taking a fast intervention without waiting the whole 30 days.
I mean, the observations were replacing the like trust in the Security Council with a 30 days with just like trust in the whatever TE manufacturer or something.
Yeah, exactly. In this limited way, and
in a
only
very
to do
particular
that
limited
and all
way,
that.
right?
Yeah, exactly. And you can still call yourself stage 1 if you do this. So
Sure.
That's kind of the.
Oh, okay, cool.
you know,
That's
appeal
the
of it.
definition expansion. I actually don't know
Yeah,
what the
exactly.
definition is.
Yeah, well, that's roughly it.
Okay.
So that's there.
Cool. Neat. Okay.
You can do this with,
neat, actually.
so say you put like a EVM smart contract VM.
Okay.
All right. You put this into a TE. You basically automatically get some private smart contracts.
Yes, exactly.
Because now you can, there's still more to do in terms of like defining the storage format and how you do with like, I don't know, things that are public like events or debug or trace logs that are there. But you can now have smart contracts that only operate on encrypted data, and therefore this is how it works in like Secret Network and Oasis, and there's several other Fala Network also are TEE-based smart contracts. And so you can take, not only do you take the VM and you get kind of a private smart contract VM, but you can even take, if you just take individual smart contracts, like you take a Uniswap style smart contract, and now you have an encrypted Uniswap style smart contract.
Right.
You get, depending on some other details, but like you can get like an MEV resistant swap contract for free. Because you can apply a rule that's like you only operate on the, even if the pool balances at the end are public after you execute it, you can do like the execution of the contract only after it's finalized. So it kind of gives you the same thing as like, commit threshold encrypted mempool and like only decrypt after the block is already finalized.
I see. Okay.
And you can get that by doing the execution of the smart contracts directly on the encrypted data in that way. So you don't even have to publish the entirety of the contracts. So you can still infer some things about the trades that took place if the pool balances are public. Even the pool balances don't necessarily need to be public. You could even conceal or quantize the exact price for this. But anyway, you can take existing smart contract patterns and apply these smart contract patterns and get a kind of generic privacy upgrade for them.
Right. Yeah, it's funny because it's actually kind of interesting, right? Like you mentioned, right? There's some stuff that you do have to think about here. So in the Uniswap case, obviously there's global information, and we know that like if you know the price before and after a trade, like totally screwed because you can always reconstruct the trade. But if you can quantize, like remove the number of bits of information, or if you require everything being processed in a batch and you only reveal the pre-contract, pre-block state, and post-contract, post-block state, you can definitely do some interesting stuff. Depending on how you do it, you could also have certain trades fail in certain cases. So if you have statistical losses, so it's kind of interesting, right? Like it's a really powerful tool for being able to do stuff like this, right? Where it's like, look, we're removing trust in the Security Council. Like, I'm not going to trust random guy number 5, running a computer in like their basement, more than I'm going to trust like Intel having like a correctly signed or attested to a thing. Which seems like a perfectly reasonable way of like kind of feeling like, okay, there's a proof reduction technique. So, okay, very cool.
This has all still been fairly like Web3, centric, but it doesn't, have to be that way at all. If you take like a PHP MySQL server,
okay,
right, that's certainly not written with like T in mind.
Yes.
But no one can stop you from running it in confidential VM.
Sure.
Especially if you also use like the TE remote attestation or like an on-chain manager of different nodes authorized to join a network and get a copy of something. You can basically I would call this maybe a decentralized front end.
Yeah, okay.
Right. I can have basically a web server where all the rows in the MySQL are encrypted, so not even the admin can access raw data if they're not supposed to, beyond the queries defined in the in the application. And you can then extend guarantees to end users that they're actually interacting with the this particular code on the PHP server, so you can get like a high integrity and privacy guarantee out of it.
Sure. Yeah, that makes sense. Cool. Okay. So I think we have a good TE framework. I'm curious, we've talked about attestations, like how do we guarantee, like what's the chain of what do we call it? There's like a fancy name for it. I always forget.
Chain of trust?
Chain of trust. Yeah. Thank you. That's the cool name. Like what's the chain of trust for these things? Like what do we assume? We could pick a specific I assume it might be better to do so a specific instance of a TE.
Yep. Yeah. So I'm going to erase this real quick, and I'm going to draw. And I find looking at the attestation, like what's in the attestation, as also a good checklist to talk about a couple of the other topics that are here.
Right. Right, because like we have like the manufacturer of the devices here, then somewhere in here is the host, here is like the developer, then there's also like the user, right? They have the like 4 things that we had drawn earlier. What is like what things get shaken, the handshake memes between what different parties.
Yeah. Normally I go and try to do this with like looking at a specific thing and try to explain all of the rows there. I can't give a good explanation for every one of the fields in the remote attestation, but I select the good parts of this. So maybe I'll write these as I think of them, and we go.
Really good.
Let me see which order I want to do these from. The first one is going to be certificate chain. Yeah, certificate chain.
Okay.
So this is going to be something that's like, there's a leaf certificate that's unique per processor.
Okay.
It's like a platform certificate. There's intermediate certificate, which is, changes sometimes, but not like per processor. And then there's the root public key. This is like Intel's long-term public key. So I mean, the main thing is that the remote attestation is like altogether a certificate. Right? The whole thing is a certificate, and like the platform certificate is like the next level intermediate certificate, and then like the root of all of this is then a public key from Intel that's like very hasn't changed, long-term public key, and that's kind of kept. So the first thing you do with a remote attestation to check it or interpret it, ultimately you're trying to make a decision whether to trust some you're about to send encrypted data to a public key that's mentioned in this certificate. So you have to do all of these checks to decide whether that's worthwhile to do. So the first thing is actually checking that yes, this is signed by Intel.
Sure.
And that involves checking this chain of certificates.
Okay.
There's other things like expiry times and revocation lists that are there. The revocation lists for these are mostly empty. And
but there's revocation lists for any one of these steps, or only for the platform level, or only for the intermediate level?
It could be for any of these.
Okay. So a revocation lists are like, we found essentially like impossible to patch bug or something.
Yeah,
or
it allows Intel to say
malicious.
like, we no longer think that this set of keys was valid, so don't consider them any further. They have expiry times as well, although I tend to think that you don't necessarily need to follow the expiry time, and that it can be better not to have your application have to go do more checking that's necessary. But
yeah, sure.
To argue that point, yeah.
And how often are these certificates rotated for the expiry?
That's a good question. That I'm not sure exactly.
Okay. Like on the order of days, months, weeks, months,
I think more
years?
than that. I would say weeks, but actually I'm just guessing.
Okay, so that's actually pretty often. I would have assumed that it was more on the order of months or years, but very interesting.
I think the most important one is like hash of program binary. Really, this should be decomposed into slightly more complicated steps, but I'm okay just calling it that for this level of detail. So this is kind of the most important thing. This is the code that was running that caused this attestation to be generated.
Sure.
This is now a compiled program binary, right? It's not the high-level source code. So this is exactly like the analogy of interacting with compiled bytecode on a smart contract chain. You know that what you're interacting with is defined by this hash of this binary code. Hopefully there's some high-level source code that's supposed to be mapping to this,
right? Ideally,
compiled to it. The job of actually checking that this source code matches this program binary, you're on your own. There's nothing that the processor Intel is doing to help you with that. That's not really the role or their thing of this. So reproducible builds comes up as one of the more fundamental topics in building systems. When I say reproducible build, establish this correspondence.
Right. Like every source code always has a unique build that no matter what platform you build it on or whatever, it always has the exact same source, or exact same source code always maps to exactly some bytecode, or in this case, it will be assembly instructions, and therefore the hash is equivalent. And then actually, very dumb question, but normally this is some binary loaded onto a slab of memory. Yep. So essentially, you're just literally hashing that big slab that just got loaded into program counter 0 all the way to however long the program
Yeah, exactly,
is.
and any of the initial data that's there.
Okay,
You know,
yeah,
and this is
sure.
typically the initial conditions. It doesn't go and like scan all of your memory when doing
Sure,
this. So this
sure,
is like
sure.
the initial state. So a lot of this is like you set up a program that, you know, in this initial state by induction, you know, it remains in
Sure.
this initial state. That's like analysis about the program, you know, that you need to convince yourself of about,
Right.
and then the attestation, you know, guarantees what that initial state was. So that's how you know
I see.
connect that
I see, I
reasoning
see, I see,
together.
I see.
It doesn't audit your code for you either, right?
Sure.
So just because here is so open source code, right? Like
Yeah, like you
also in
gotta go
smart
read the
contracts,
thing,
right?
ideally,
So you
or
kind of
trust
view all of
somebody.
this kind of in the context of, you know, auditing as well.
Sure.
Sometimes for like silly reasons, like, well, and some good reasons, like reproducible builds are hard to guarantee in all cases.
Oh, interesting.
There's
Actually,
this.
yeah, what are some examples? This is very dumb of me. I mean, obviously,
don't
like
worry.
it could be the case, but like, you know, in my head, I think like, LVM is doing some stuff, you
Yeah.
know, and does some magic optimizations, and like out comes like a nice little binary. Sure, but what are standard ways in which like reproducible builds fail?
Sometimes there's like compiler options that basically like pick a layout dynamically, and then it like can just essentially be
interesting.
based on, I don't know, race conditions or something pseudo-random or timestamp or things that are like environmentally different in the, you know, environment that it's running.
I see.
Usually there's options where you can go and turn those off if you're building, especially if you're taking like random, you know, PHP legacy packages, then like it's hard to go trace down and, you know, fix all of the, you know, dependencies for the rest of those. If you view this as part of a whole auditing process, like I need to convince people, you know, something about my code, sometimes you can make up for the lack of reproducibility in builds just by, like, you can audit program binaries, you know, as well.
Sure.
So, you know, it's not that reproducible build is the only way of getting confidence about what the compiled program binary does.
Sure.
The goal is to get, you know, confidence about what this compiled program binary does. Reproducible build is kind of like, you know,
one approach.
one of the most
Sure.
crucial, you know, things, and you get as close to it as it can.
Right.
There are things like timestamps that are, you know, injected into there. So a lot of times you do is like when you build the program, you like kind of fix the system timestamp to 1970 or some, you know, fixed value. And
Right.
then, you know, it's like you have to. It's like the one dependency, you know, fails to honor this, and there's no easy way to go change it. Something like that.
I see. Sure. Okay.
There's even these things, you know, the reflections on trusting trust.
Of course,
you know,
yeah.
famous paper. So like, well, who compiles your compiler? So typically you have trust anchors,
Yeah.
and you say, well, I will regard the, you know, Rust compiler at this, you know, top of the month, you know, date, major version or something as okay, and I'm not going to make it, you know, my problem to go
check
trace
it out
down
or
all of the
whatever.
things about how
Right.
that was built, and, you know, in the first place, although arguably you should. So, you know, that's kind of this whole separate topic, but, you know, the fact that the attestation includes at the program binary level kind of reminds you to go, you know, check with that. There's an application-defined payload. This is, I think, the fun part. So this is something that the application that requests this attestation gets to specify. And so this is somewhere where, you know, as an application developer, you often make up something that, you know, will go here that makes sense.
Sure.
A really common pattern is that you basically generate a private key in your program, keep that safe, include the public key in this application payload. Now you generate this attestation once, and it kind of like forwards your trust on, you know, it creates kind of now this trust in a public key.
Sure.
And now you can take signatures from this public key as having come from this. You don't have to check this remote attestation format all the time. This pattern is especially used for, you know, Web3
Okay.
things because for, you know, kind of silly reasons. These are just certificates, but like Solidity is kind of a pain at just like,
Yes.
you know, string structure, you know, parsing. So that's kind of noisy. And the signatures that are used in, you know, this ecosystem are like the wrong ECDSA curve,
Oh,
you know?
classic. It's like P256 S1 versus K1 or
yeah,
something.
exactly.
Sure. Yeah.
Exactly. So it's slow, right? So it's
Sure.
like gas expensive.
I see.
So if you want to do an on-chain check of this, then you like do that once and forward it to a real ECDSA key that then you can check, you know, thereafter. Now, like maybe every block you want to output something from the enclave, you'll sign it with the public key that was, you know, added to the chain of trust basically once.
Oh, I see. Okay, so inside of the source code or / whatever, like we have. I'm just making sure I have my
Yeah, you're on the right
mind
track. Keep
wrapped
going.
around it. Right, we have the private key, which obviously like then results in some public key that we can then use to verify. And the point is, like the observation is, look, okay, so long as nobody has access to this like private key, other than ideally the like secure enclave, which at some point is like, you know, deigned to be good. we can then, whatever we sign afterwards for that private key essentially can be assumed to have come from this, good. Like, as long as we've checked it once, somebody has checked it once, and the rest can simply just be verified by like having that public key, checking that everything has been signed with that, or has been signed with the private key corresponding to the public key or whatever. Okay. Okay, I think I roughly get it. Yeah, because it's like essentially what you're saying is like, look, check it once, we're all good, everything after can be assumed to be good, and then now just only verify that signature.
Yeah.
So there's like a weird initial condition setup time. Thinking about this as like a source code running on a blockchain that is verifying this. There's like a single time setup when you first initialize the contract, and then you check this thing along with like the map to the public key, and then forevermore you may simply just check this.
Yep.
Okay.
Absolutely.
Cool.
Yeah, that's exactly right. And this is almost like a general purpose kind of approach. So like you can almost do this in application, maybe every application should do this. You do this in like a shim kind of way, regardless of what particular app you do. And now you can just the rest of the time think in terms of these public keys. You don't have to worry about the rest.
Nice.
Of the
Okay. Yeah. Sure.
All right, this will be the last one that I go over in attestation, and it's an interesting one. This will be a little more nuanced, but it's kind of good. Is you have like CPU configuration. So you have some metadata that describes which processor family you're using and what's the version of the BIOS that's there.
Okay, sure.
And now what's interesting about this is the Intel chips are mostly software. Like they're mostly microcode. x86 is a virtual machine language. It's very, separated from what actually happens there. So basically, when bugs or vulnerabilities are found in the processor that undermine, these isolation guarantees, they go patch it, and then they release the patch as downloadable content you can use to upgrade your processor. And so what they publish these TCB infos, which is like they have one of these for every processor type. So you go get like one for each processor type. It's like, I don't know, 40 odd, processor families that you get in Intel, and they publish a little like JSON file of TCP versions for each one of those.
Okay.
And in each JSON file is an array of different versions for different BIOSes. And then they also include like good or not, basically, like trusted or unsafe, and
or
like
unsafe,
with some,
and you should not be trusting this. Got
good, bad.
Okay,
right?
Interesting.
And you can get these from an API that Intel Attestation Service publishes, but they're signed, so
well,
you
I
can
assume
kind of
the
hold them
same key
accountable
is...
to it. Yeah, exactly, kind of a related, exactly.
Or a related key, right? Something that traces all the way back up to...
It's a fun little diagram that is that little thing, but yeah, absolutely, goes to the same root for sure. And so what happens is sometimes you get a new signed TCB info in which some of the records change status from good to now no longer good. And that indicates that they're now, disclosing that there's like a vulnerability associated with this outdated version of the BIOS. And hopefully by the time that happens, all of your cloud instances have upgraded.
Sure. Yeah.
And what you also now have to do is it's called a TCB recovery. Meaning like it recovers the processor from in a bad state to now it has to go through this like that's a time when it redoes the certificate, like platform certificate, and it can now have a CPU configuration that now matches a currently known as good status. But you have to write off whatever you had before if your app was still running on an outdated version before you need to know to do this. And you have to basically, so part of validating that this attestation is appropriate before deciding to do it, you need to know that you're talking to something that, to the best of your current knowledge, is still considered, in the good status. So you need to compare it against these reference values.
Right. So you need to just every time you do this or this, now go to the Intel website, figure out exactly whether you're running a bad version, right? Figure out the root of trust is good, and then come back and be like, cool, checks out or does not check out, and we have other problems.
Yeah, exactly. That's good.
I see.
There's a project that I like a lot called the Automata On-Chain PCCS. The PCCS is like Platform Collateral Caching Service.
Oh my.
These are called collaterals. They're things you compare against. I think it's a confusing name, but I call them TCB infos.
Okay,
I don't know.
Seems fine.
So normally you go and fetch this from the Intel Attestation Service, but that's a little bit of like an unnecessary man-in-the-middle kind of vector. Like you wouldn't want Intel being able to, or on the hook to be pressured into giving you a wrong version of this to confuse you while showing everyone else, the normal version.
So naturally, put it on a blockchain.
Put it on a blockchain.
This
Use
is
a
good.
bulletin board.
Yeah,
It's
okay, great.
if you know like the certificate authority system and the certificate transparency project, it's the exact same analogous thing. There, it's like you want to browsers enforce this. Like so, in order to prevent certificate authorities from man-in-the-middling one targeted laptop with a certificate that no one else sees, browsers will not trust the certificate until they've like bounced it to like 5 other servers and like they know it's being like tracked.
Oh, interesting. I
And
actually
so
didn't
if you
realize
get
it.
man in the middle and you have a modern browser that supports certificate transparency, it was a big like Google campaign to get this, widely adopted. So your browser now is defended against being singled out and no one, getting in trouble for it.
Sure.
Like it's like the dash cam, of having trusting a set of certificates.
I did not know that actually. Okay, that's cool.
And so it's the exact analogous thing in browsers and TLS is for, this and like the on-chain record of these.
Sure.
And Intel signs it, so it's not like they're trying to make it hard, but like why have to fetch their, from an API when you can already have it documented in a bulletin board and referred to by smart contracts.
Sure.
So, that's that.
Okay, very cool. And this is it? This is roughly all, I mean, this
That's
seems
roughly it.
pretty
That's all the good
complete.
parts.
Yeah. I was gonna say, okay, cool. Any last thoughts on attestations before we move on to specific examples?
No, I don't think so. Yeah, I'm good to go.
Cool.
All right.
All right, next up.
Okay. All right, so I now want to go over this kind of architecture of applications as a TEE coprocessor for a blockchain. And this gets into some of the like separation of duties about like what blockchains are good for, how TEs require blockchains, and kind of vice versa for the privacy.
I see.
Kind of thing. In a nutshell, all cool applications of TEs involve a light client in the TE. So you use the blockchain as your source of truth, like command, manager. TEs don't have any like redundancy, right? It's just a processor. The untrusted host can power off the machine.
Yep.
So you are certainly going to need multiple TE nodes if you want to have any redundancy, like failover ability for your application. And then if you have multiple of those, you're going to have race conditions and an issue of like which one's active at a time. And so you need a bulletin board or, consensus. Otherwise, just assume you have external. There's already blockchains, so use those. And, have that be like the coordinator for TEs. So basically a really common pattern for this application that addresses this is to have the TE running in a controlled mode where it follows instructions from a smart contract.
Okay.
And so it inherits like the sequentiality, like consistency guarantees, censorship resistance guarantees from the blockchain.
I see.
And these are then like stateless worker nodes, whatever, that just do whatever the smart contract tells them to do. So what you'll have is like in each TE coprocessor program, it has a light client. The light client observes the smart contract. And I guess I wanted to set this up for like, we're walking through, I guess I'm not even going to try to write pseudocode or anything, but like, imagine that the goal of this is going to be a sealed bid auction application.
Okay, sure.
That also gives, say, post hoc security for the trades. Like, so anyone who didn't match, their bid is going to remain private.
Okay.
And I'm saying it kind of carefully this way just because maybe the first way that you would do an auction most of the way there is just a commit and reveal auction. That's like the classic Solidity tutorial smart contract, a sealed bid auction with hash commitments.
Yep.
But then, well, I mean, the first problem with sealed bid auctions with just commit reveal is like the guy can just not reveal. And then over collateralize and stuff gets around it, but it's kind of messy. And even if you are okay, whatever, crypto economically or do secret sharing or something, so everyone has to reveal. If you reveal, then everyone, even the winner, maybe the winner's inherent, you have to make some on-chain action that's going to be visible. So winners say that's okay. But everyone else who didn't have their trade met
also has to
reveal. And like that's like unmet demand. Like, someone wanted to buy this and was unsatisfied, so they still want to buy it like at that price. So it is like strategically, even though the auction's over, the unmet demand that's not, there is still, strategically relevant. And exactly.
It doesn't matter in the single shot game, but it definitely matters in the like many shot game, which is like real life.
Yeah, exactly. So we have chain smart contracts on the chain. Don't know exactly what kind of visual language I want to draw here, but whatever. There's a blockchain.
Beautiful.
what we would do is have, so first of all, there would be many of these nodes. Maybe I'll get to like, let's say like other TEEs here. We can talk a little bit about like what it looks like for them to, join a new TEE node to the network. These will be like ones that can be a backup for this one in case it goes down.
Okay.
One node is going to do something where it generates a private key. I meant this to be, what do we want to do? I'm going to update the boundary of this to include the private key.
Okay. So this is essentially, this is not a TEE, this is a single TEE.
This is a single TEE, yeah.
Okay.
All right, TEE compute node.
Yep.
I don't know, the TEE coprocessor node. Not using consistent terminology, but the concept's what matters here, right? Okay, so the private key is here. Public key would get stored on chain.
Yep.
The remote attestation would either be directly checked on chain, or just it has to be considered part of the like constructor and code definition of the contract. Like you trust the contract because someone's audited it, or you can audit it yourself. So look at some code on GitHub. You should also check that the attestation for the first compute node is also included. Doesn't necessarily have to be on chain, but checking it as part of the audit surface. It makes no sense to think of it like that. All right, so this has the public key for which the private key, just like we said, like the attestation would include that public key.
Yep.
So now that's the public key that if you encrypt messages to it, the TE and only this TE can access it.
Yep.
And now if the user has a private bid, they would encrypt under the public key their bid and make a ciphertext.
Yep.
All right, so now this is encrypted, so only the TE coprocessor can access it.
That's right.
You would then post that ciphertext on chain so it gets recorded in the smart contract. Now, this smart contract would also set the timing rules. So after like the deadline of the auction is collected or is reached, all of the encrypted bids that are collected now have to be processed and treated as a unit. Kind of like skipping ahead to like the implied kind of like trust model here, but like we don't want the host, wouldn't want users just to directly connect to this TE as a service because that has to go through like the router and the network, which is all controlled by the hypervisor.
Right.
So the untrusted host could selectively, drop packets or censor bids.
Yeah, it could be like, I know Andrew, and I don't like that guy.
Yeah,
Sorry,
exactly.
Just gonna drop the bids. Sure, 100%. Okay.
But if they put it on chain, then you either have to process everything that the light client says is you're supposed to on chain, or nothing at all.
Right. Because you're just going to take the head of the chain and you're going to be like, look, you better process everything before that. And the head of the chain could be, you're not going to give a stale head for some reason because the light client wouldn't accept that or something.
Yep, that's exactly it. And then, when the result, so it gets all the data, it can compute on it because it has the private key. It has to compute on all of the bids because it's following what the light client says is the smart contract state. And when it writes the result back, it can sign the result with, the same private key. You can, check it's now a signature coming from this. So I know it had to be generated by that program. I already have the definition of the program, so I know, it did the correct of the auction.
I see. Okay. Got it. So, this is the cool part here is like essentially this guarantees that the number one is people aren't just rejecting your, bids, obviously, because they get posted on the chain and people ideally don't. You're assuming some honest majority thing already there, which is great. But the number two is, you never have to, like the only time you ever reveal a bid, actually you don't, technically I don't even think you need to reveal a bid if the chain is privacy preserving, but if it isn't, then you just reveal is whoever won the auction, right? And I guess in some sense potentially, actually you don't even need to reveal the...
Maybe everything is in the TE, and like there is no global state to have to reveal. And
exactly. So exactly. Well, you will have to reveal if you're using the blockchain for the actual transfer of value. You'll have to reveal that. But other than that, I mean, like, look, if it's off chain or whatever, that's fine too, or elsewhere. Very interesting. Okay,
absolutely.
I see.
Now, I kind of claim that part of the reason to have the smart contract, this is already pretty well motivated just by the censorship resistance. So, maybe that's enough. But I mentioned, like, okay, so this one node generates this private key at first, but we want redundancy. So we want some way that if this node goes down, other ones can join. Could also use the blockchain to basically have like an onboarding process. So this node doesn't have the private key yet, and all the bids are encrypted to this key. You don't want to make everyone like rebid, or you don't want this guy to be able to crash and cause other people to go and get like a peek of it this way. So you could have this node do an attestation and
that too is cool.
Some kind of onboarding. Maybe it generates its own private key for receiving encrypted data, and then other nodes that already have this private key encrypt this private key to the receiving public key of this, other one. So this is enc pk prime if this is like priv key.
Prime.
Yep. Yeah, then public key gets included on this onboarding, message. This PK is this onboarding message that I meant, and then, the encryption under this new one of priv key, the main one, gets posted on chain, and so now this node, is able to join it. And it doesn't matter how many of these nodes they are, because the, input-output is defined by the smart contract. Like, you have to process exactly all of these. So even if multiple of them do it, it would be exactly the, same.
Right. Should be exactly the same result at the end of the day, and the smart contract would trust the result, or whatever method we are using to transfer value should trust the result.
And now you can have as many of these workers, enough. It's kind of in any trust model then, right? Like if even one of them is capable of running, then you'll get a result, posted to the chain eventually, and the auction settles appropriately.
Very interesting. Yeah, there's an implicit trust model here too happening, where it's like this like chain of trust is like. What do you call it? Like is like transfers, right? So like you start with this, you then create a new chain of trust, the private key then gets transferred, and so on and so forth. So which is
transitivity kind of.
Yeah, transitivity. Thank you. That was the term I was looking for. I could not. Okay. Cool. Okay. I mean, this is a pretty cool application, right? Like it's quite difficult. Nobody really knows how to do this currently with even like standard ZK proofs, right? I think there's some MPC approaches that actually are somewhat interesting. But this is one case where like a TE, it's either, I think the only ways that we kind of have good ideas of how to do this is like something ridiculous like use FHE, which I guess is possible but quite difficult because these things are huge, or use a TE and like, the worst case, whatever, someone leaks, your historical bids or something, but in the normal case, it's fine, right? Like, it really does not matter at all.
I'd love to be able to dig into this and do like a short table comparison.
Let's do it.
Of like MPC and FHE for that. I'm gonna have to go look for a slide on that to be able to do it. So maybe we could do that after a pause. Yeah. Okay. All right. So since you brought up ZK and FHE, MPC, others, I want to try to describe how all of these can kind of. And I went through this commit and reveal example. Just kind of want to draw like, one way of viewing like how these all fit together. So it'll still be kind of a similar thing where we assume a blockchain is available for users to be able to put bids on. And we have an auctioneer who's party that's involved in carrying this out, and we'll instantiate this auctioneer in a whole bunch of different ways, like with ZK and MPC, and kind of remark on the trust model that's involved with it. So the first way of doing this of just commit and reveal is like the parties send their, hash of their bids to the blockchain, time elapses, the auction's over, it's like deadline. And then they, reveal the bid. And so for the losing bids, we covered the strategic information that's there. In this world, commit and reveal, like all of the bids get visible and visible to everyone. We did this paper like in 2015 now, I think, called Hawk, which was basically how to improve on the commit reveal auction by adding ZK as well. And so the idea would be that you don't just rely on users to, voluntarily, whatever crypto economic incentive to reveal their bid and forfeit it. So instead what they do is they commit the bid. There's, for kind of a, detail reason, slight improvement in trust model to do it this way. You commit first, then there's a commit deadline. Then there's a phase when you send the encrypted bid. And it's encrypted under the PK of the auctioneer. It contains the bid, and you also include some ZK proof
of the
that it's actually to the, the auctioneer has their priv key. They put the public key on chain, so that's that of the auctioneer. And now when the auctioneer does these, it's kind of the same thing. All of the encryptions are valid. Only the auctioneer can decrypt them, but the auctioneer can't say, oh, I didn't get it, or oh, the encryption wasn't valid because like the smart contract checked the zero knowledge proof that it was valid. So then they do the decryption of all of the bids. They have to put the result, of all of the bids there, and a zero knowledge proof that the result is done correctly and covers, all of the bids that's there. And this is like the best you can do with just ZK.
Oh, interesting.
And The only thing that's bad about it is that the auctioneer still gets to see all of those residual bids. So now the auctioneer has that, hidden alpha about all of the unmet demand, implied by all of the bids that weren't matched. And it was really dissatisfying in 2015. I think the end of that paper is like, well, you could instantiate this with MPC or something else later. Or with TEs, right? And so then that kind of was the, research direction that kind of kept going there. So, we could exactly do that, right? The next thing is to, and this little detail is just input independent. So by having the commit phase and the encryption phase separately, the auctioneer can't do the decryption before the, no new commitments to bids are accepted.
Oh, I see. That's why, got it. Yes, that makes sense.
And now this is kind of the semi-reveal. You still need a security deposit or something you forfeit if you don't put your encrypted bid there.
Sure.
So that's how far you can push the zero-knowledge proof. The problem with zero-knowledge proofs is they have to be made by a prover who has all of the secret witness data. You can replace this auctioneer with now, instead of it just being one party as the auctioneer, you can instead make it, several parties that do some, K of N secret sharing, or MPC. So they, compute all of this. There's two notions that mean the same thing of MPC plus snark, is either, I think, people now mostly call this co-snarks. An earlier term for this was auditable MPC.
Okay.
I don't like the name co-snark for it because I think it makes it seem like it has more in common with snarks, whereas I think it really has more in common with MPC, trust model-wise, because for privacy, you're depending on this, majority trust of this committee, right? You have to trust this committee. Still, you get the input independence guarantee if you do this, and still you're not relying on them for integrity at all if you're producing these zero-knowledge proofs. But your privacy depends only on the trust in those parties. If they all collude, no one can check whether or not they all colluded. They could just silently take this alpha and trade on it, or collude, trade it away. So that's kind of what you're left with. Now to add FHE to this. What FHE allows you to do is basically, normally with this being MPC, there's a lot of communication back and forth, right? Stand-in bad drawing for lots of, maybe another way of doing it, it's a complicated protocol, lots of rounds of interaction, to do this kind of thing. It's compute expensive, bandwidth expensive, gets worse with the larger number of people that there are. So when you add FHE to this, what you do is now have untrusted FHE compute workers. All right, and this can be anywhere because you don't have to trust it. It does the computation. And now it just sends the encryption of the result. And typically something like a ZKP that this was done correctly as well. Right. And now you still have these K of N nodes. It's basically these K of N nodes carry the decryption key. So FHE is still a public key, private key crypto system. There's a decryption key to get the encrypted, to decrypt the result. So you would have these committee of nodes secret share the decryption key.
I see.
And the key thing to stress here is that FHE didn't change the trust model. You're still relying on the committee trust and privacy.
Yeah.
What it did do is shift the computation workload elsewhere. So you did it as a performance improvement relative to MPC.
I see. Okay.
So I consider this a terminology pet peeve because, MPC maybe is rightly associated with this, well, you have to trust this K out of N nodes threat model. That's not cryptography. That's just how do you select this committee of nodes? Right. What makes you think they're going to be, honest, even if there's no objective way to prove that they, didn't collude?
Sure.
And so, if you just say co-snark, it's kind of hiding, the co is the, K out of N assumption for privacy that's there.
Naturally.
And if you say FHE instead of MPC, that doesn't, quite cover it because it's doing the performance improvement, but the trust model still for privacy still comes down to the committee trust about the decryption key.
I see.
And you can use all of this in conjunction with TE as well. So, I think a kind of best practice way to do this, if you can afford the cost or the, untrusted compute makes this a good deal, is these MPC nodes or co-snark nodes, have them run into TE as well for a backup. And that way, not only would the MPC nodes they'd have to choose to collude, and they'd also have to be exploiting, whatever vulnerability in the cloud plus the hardware model to be able to, get away with it. So then it's the TE node is kind of, helping the MPC nodes, be honest by making it pretty inconvenient for them to be able to
like any one individual party
casually
to...
just be tempted to do it differently.
Right,
It's
right.
like the locks make good neighbors kind of thing.
Right. Yeah, and in that case, like a trusted FHE compute part is fine. I mean, it doesn't really give you that much here. Okay, I see. And the question is, so essentially the best possible thing is like combine everything, like throw it all into like one big pile and like stir the pile. But I guess there's some high stakes auctions. It might be like quite good to do that. But like most of the properties that you have out of here, which I think are interesting, and one of the difficult parts of auctions is the fact that you have to commit to the thing, which means you have to have the money to be able to actually do the payment, and that reveals some amount of information about the underlying thing, and in a public blockchain on a private one. Yeah, okay, I see. I mean, it's a good application, and in general, right, you can think of like adding TEs to the sauce to kind of improve security guarantees by having this like. Now it's extreme. Not only is it inconvenient, but it's extremely inconvenient for even one party to kind of add this decryption thing. And so naturally, the K of n, would have to have, like you said, people exploiting each of these things. 3 layers in to be able to get this to work. Okay, yeah, makes sense.
This auction example has this quality of being based on like multi-party information, or global private state is kind of the name for this. So there's no one party whose view includes all the information necessary to close the auction. So if there's no like one natural party who can just do the result locally and prove something about it. Lots of applications, don't have this quality, and then you don't need to go to MPC or TEEs for processing on it. Like FHE is often used in this like outsourcing example where there's a data owner and it's their data they want computation on. They just don't want to do the computation, so you outsource it. But the guy who provided the data is also the one who needs the data, so just have them have the decryption key for themselves. But that doesn't make sense in an auction, just and then lots of other examples. I mean, arguably most things of interest where there's like people involved, that's why a blockchain might be necessary, or that's why it's kind of interesting. Then if you need this shared private state, you really have to turn to committee trust and or trust in the hardware and cloud operating kind of environment, one or the other or both of those. But mainly it's not that there's like, otherwise cryptography is not going to bail you out of it. You have to kind of accept one of those. Okay.
Very, very cool.
I guess there's one other, the only other thing that I wouldn't, mention there, and actually I'm not sure how I'm going to be able to draw, a thing for this, but there's the idea of cryptographic obfuscation or IO indistinguishability obfuscation. This is like to FHE what FHE is to like ZK and the rest of, cryptography in terms of being, more expensive. So this is considered like not practical, right now. And I guess I won't go into trying to, describe the rest of it. You should get someone to talk about obfuscation, though, for one of your modules. You would do a similar kind of thing, though. It's interesting because like this also doesn't give you like, one-timeness. You can't it gives you an obfuscated circuit that you can run, but it can like embed a private key in it, and you can only run the function that it was generated for. But still, there's like problems. One is like, this needs a trusted setup, like who's going to generate this circuit and put the things in there. And nothing stops you from running that function multiple times with different inputs. So you would actually still need to pack the circuit you put in here. You would have to pack your light client in it and still be relying on an external blockchain for the statefulness.
Because I guess this is always like a pure function.
Exactly.
Fine.
A pure function, and you can't compel someone with that function, to run it multiple times.
I see. Okay.
Yeah.
Very cool. Yeah, but we should probably get someone to talk about I/O. I don't know if we have somebody. I don't think so. So that'd be fun.
Oh, yeah.
All right. Okay. And then last but not least, we've talked about all the like positive ends of this. Like, I think it's time to talk about the pitfalls.
Yeah, absolutely. I'll erase this.
I guess we talked a little bit about some of it.
We talked quite a bunch. We talked to my satisfaction about side channels, actually.
Okay, perfect.
The more interesting thing I want to talk about, it's not just, it is a pitfall. It's kind of just something that you have to deal with, is how to do upgrades without getting stuck. And actually, I don't have a slide immediately for this, so I'm not sure actually what we're going to draw for this. I can certainly describe the problem. Maybe I will just talk about this for a bit and then come up with what to draw. So, let me think about it. I think I do know what I want to draw for this. So say we are in Do I want to motivate this with like an auction example? It's kind of tricky because like an auction sort of happens and has a natural conclusion.
Yeah,
I mean, if I say this is like a dark pool,
I was
like
about to
with
say
long,
maybe like a DeFi example or
yeah.
something.
Okay. So I want to set up a setting where I have like persistent state, where I'm going to have long-lived state, and I can't just like say, oh, like game's over, everyone's going to like put their data back in again. I really need it to persist for a long time.
Okay.
So I'll say this is like a dark pool with standing orders, and like I can't just cancel all of the orders. I really need to like keep the orders preserved, to be able to do that. What the TE can give you, and what we just drew with that coprocessor example, is like I have this remote attestation that covers the hash of the program code, and I encrypt my data so that exactly that and only that program can access it. Drawing like program, version 1 here. Immutability is like what you get then by default there. But in the same thing that happens with smart contracts, like no one likes immutable smart contracts, right? Like EVM smart contracts are immutable, like except for one, right? But all the rest of them are immutable.
Sure.
But then no one likes that, right? Because you want the ability to upgrade contracts. And so you build like a proxy layer where you like build in, on top of the immutable substrate, you build on like a migration method that allows like the
pointer to like point to somewhere else before you're able to like
exactly. So you like build in an upgrade mechanism. So the same pattern happens with TEs. Like you don't want to be pinning yourself into like only being able to run a single version, because then that's too rigid. You want to add a feature or be able to respond to a vulnerability or something in that. So what you typically then build is some migration mechanism. And if we had that idea that it's a coprocessor, so there's a smart contract here that every TEE node, if it wants to join the network, it has to check in and pass this attestation challenge. It's the smart contract that's in control of the like coordination layer, like control plane messages. It's like the orchestrator of these TEE nodes that are running. So it can simply have, in the same way you would have like Governor Bravo contract or something, like a DAO vote to approve whether there's an upgrade allowed or not, you can do the same thing. This can say now it's not just a particular version, but like the current version, and that can be updated by, a DAO vote. So this would be like this stores V1, maybe this also stores V2. And so this node, before deciding to send, I guess I'm now kind of like referring to that, step from the previous one, like when we encrypted the secret key to the new private key of this new TEE that's running the version 2 of the program, and now it wants to receive a copy of the secret key encrypted to itself. This one has to decide whether to do that based on the attestation that shows up here, use the smart contract to determine whether this version is allowed or not. Now, the problem is that you still now introduce, like, in the same problem with smart contracts, if you just have, like, only owner, like whoever's the owner of the contract is some EOA jerk who can then just add a new, method to it or add a new allowed program, that's not great. That's just still like a central party. If you don't use the smart contract one at all, you just have like code signing or something, then it's maybe even worse, because someone could make a signature to authorize it, but not even show it to anyone.
Just like sneakily do it, exactly.
Just like sneakily do it and output all of the bids, and no one would necessarily know. So at least you should like post, at least you should enforce in the structure having to post the update on chain. And even then you probably want like a due process kind of thing where like it's got to be there for some notice period, so maybe users can like retract their private data and keep it from being able to be included. All of that's a lot of extra hassle. It's not extra hassle that's like put there because TEEs made it difficult to put it there, which you can tell because it's the exact same problem inside of constraints that you get in smart contracts, and the hassle of live deployment of smart contracts. Like you have to confront all of this. So it's in no way unique to TEEs. I mean,
it's in some sense it's also the same problem with like anytime you do an upgrade for anything, right? Where like the upgrade path is deterministic, and what's cool is like when you're running a node, in some sense the upgrade path is social, right? Like surely everybody just runs the same piece of code, but we trust the fact that like most people are honest to like, do the due process of moving up to a new version of the code, and then they just run the new version of the code, and like consensus all works nicely, assuming that everything is good. Here we have like an intermediate layer because like, the TE has no notion of like social consensus. It's like, look, my social consensus comes from like is derived from a smart contract or something, right? And there's like an attestability like piece in the middle. So.
My grad student Nurla is working on this paper about like rage quits for this upgrade mechanism, which is she presented it at like an Astria Day talk. So there's a talk already about it, kind of already up. But the basic gist of it is, like you said, like you can rely on the social consensus, but I like this idea of avoiding the tyranny of the majority or something.
Yes.
Like I don't want to, and this is consistent with how L2s and stuff work. Like the rage quit mechanism is how even if the majority of the DAO votes to like cancel all of your coins,
right,
you're allowed to withdraw your, the mechanism set such that you can like uncooperatively withdraw your coins, before the upgrade takes place. You get to like take your coins and leave. So, same kind of notion, but now with your private data, not just your coins.
Right.
But, it's the same thing. So this is drawing attention to a part that's not, it's part of the whole TE world, because TEs bring in this kind of immutability on top of dealing with private data. And that introduces a bunch of like it's hard. I don't want to say to someone, to your TEs you have to like deal with this whole thing kind of right in the way. But again, same thing with smart contracts. Like that, this all stuff doesn't show up in the like Learn Solidity tutorial, but it's part of understanding how the systems work in practice. So yeah,
that's right. Oh, cool. And then I guess, I don't know if you want to talk a little bit about replay attacks.
Yeah, sure, absolutely. And I think we can do it good. So we talked about side channels. I mean, these are all under pitfalls. I call them pitfalls because it's not like something that you need to invent something around. It's like we know what to do to prevent them. But if you just kind of port code without thinking about it much, these are like the first things that you're likely to run into. We covered side channels really well. Upgrades I like talking about. That went really quick, but I think it was, pretty clear. So let me see if I can make replay attacks, make much sense. And actually it goes back pretty easily. I think I'll keep this pretty simple and just draw, back to what we had before. So this is the TEE. You also have the untrusted host on the outside. And we covered things like the, encrypted RAM is here. Network, I think we kind of implicitly talked about. I'm forgetting what thing, but like, which is relevant for privacy and stuff too. If you're going to just have TE nodes connect to each other, like the IP address has to be, visible revealed, to the, yeah, exactly. And, disk was there. You would have like an encrypted disk typically where the key for the encrypted disk goes here. But nothing about this ensures that like the disk doesn't get replayed. So if you just use some code that like is your PHP MySQL not intended for TEEs and you try to get it to here, it'll work. And if you don't, you run it in ordinary mode, everything's going to look like it's working. But the pitfall that you have is that someone, the hypervisor even could, rewind the disk to an earlier state.
Yes.
And typically the way that the disk encryption works is like it's authenticated encryption. So each block of the disk is encrypted with a tag that depends on the location of the block.
Sure.
So you can't like copy a block from one place and like replay it, in another block.
But you could take the whole...
You could take a whole block, a previous version of a whole block, and replay it. And that's like out of the threat model of the way that the like encrypted disks are going. And pretty much the only way around this is to have like a Merkle tree. So like if you have like a Merkle tree over all the blocks of the disk and like maintain that, then you have this like freshness tag kind of availability where your TE can know that it's getting the the current version of the block each time. And maybe a decent design thing is just don't use the disk like where you had the disk, instead go to the blockchain for all of that. Use like a blockchain as your external consistency log. That can be kind of inconvenient, or just like within the T keep a Merkle tree over all of the things, but now that's not something that like the disk kind of does by default. And whether this is detrimental to the application or not just depends on the details of the application. And I kind of show this for disk here, but I guess sometimes you have like an external database, and then even if you use same thing, even if you use the TE for like the encrypted rows of the database, that's fine. But the database state, if that's just external, on its own, it's not going to bring these rollback defenses against that.
The TLDR is like it's not clear if you have a fresh state or if you have a stale state, and that stale state could always like there's no easy way for you to distinguish this, at least not without, for example, a blockchain or something of the like. Because you have no notion of real external time with respect to a piece of data here, right? Yeah,
exactly.
Yeah. I mean, it's also an interesting thing. I mean, we get pretty meta about this, right? You could imagine that like the network chip itself has like a TEE. Right, and then that thing essentially guarantees that like network inputs and outputs are. I mean, network may be a bad one, but a database might be like in some stick that itself has a TEE which is trusted.
Yeah, absolutely. Where you might build your database out of out of the TE for each node as well. Yeah, sure.
Right. Or so all sorts of, like, it's kind of interesting. Like, all of these bits and pieces can be fit together and blown apart and all this stuff. And you could have intermediate TEs and, like, like the camera case, right? There's like, you were just mentioning this.
Yeah, the Sony camera Sony cameras are a hardware TE. Like the new Sony cameras have a TE mode where they will output along with, like in the metadata with the camera, they include a whole signature chain up to Sony.
Right.
It's even more than that. It has like also timestamps, like the time that it was done.
Yes.
I don't know how it knows the time, but
I think it's GPS.
Something like that. Okay, and altogether this is meant to be in the kind of tamper-resistant, thing. Still have to trust the manufacturer not to fake it. They also include something like a range image. I was just reading their like docs, on this.
Wait,
so there's like a range image, like depth image.
Oh, really?
Like a time of flight sensor or stereo processed kind of thing gets included in the metadata of the normal image, so you get some kind of like extra, stuff. All of which is covered, as part of the signed, data for all of that. This is in some like closed beta where only journalists are allowed to have access to it, and it'll roll
Yeah, it's like you have to have like a server or something inside of the like your org has to have a server which they then use to like assign the cameras or something. I remember trying to read through it. No, it's cool stuff, right? It's like very quickly, right? It's like I think very early on, we were also just talking about this, during one of the breaks, is TEs were used as like kind of quote unquote only bad. I'm gonna go out on a limb and just say that of like DRM, right? And like DRM like prevents you from using like
anti-consumer tech, anti-general purpose computing tech.
Exactly, and it's like now it's kind of fun because TEs have become this much more general platform. It's like actually like no, you can use exactly the same technology to like be able to run whatever you want on somebody else's like Amazon servers, like trusting Amazon, for example. All right, so it's kind of an interesting
Yeah, it's a pivot that's like along the kind of basic principle of like use apply constraints on like the powerful and to kind of like allow that. So you don't want to impose DRM on end users and deprive them of general purpose computing on their laptops, which was the original kind of use cases for SGX. But now it's much more the other way. Use it to like constrain the already powerful. So constrain the cloud providers for that. So. I think one of the reasons why like TEs went through like a very negative, hated phase was a lot because the first use of it was this kind of thing. People rightfully were against even the trust model aside, just the use of that is anti-social, anti-consumer. That's bad. But now that it's mostly deployed in clouds and for servers, it's like a whole new purpose. And now so I think that's really great. I guess another thing kind of like on this trend, I didn't meant to earlier mention the phrase like confidential compute, but when I drew that thing that's like the TE and the cloud and all together, that's you view as kind of one two component unit. You just call it confidential compute when it's like the TE hardware and the kind of cloud service that they provide along with that. And that trend's really increasing. So it's not far-fetched to expect that like most hardware, like routers, middleware, other kind of things, seem likely to have this kind of approach to them by default. So it's not even really contrarian anymore. It's like a increasing direction that's pretty broadly already and only increasing so supported. And clouds and processors and other hardware increasingly.
Cool. Any last thoughts of the instructions? Because if not, I think...
No, I don't think so. This was awesome. Went great, yeah.
Yeah, thank you, Andrew, so much. And thank you all for listening to lovely, CK Season 3, and stay tuned for more.